There we go. 8 o'clock, we should probably get started. Yeah, last time we went through kind of what quantum states are, some quantum gates, some quantum circuits, and then ended with teleportation. It was a lot of information to cover in one lecture, so I apologize. I kind of had to go a bit fast. Yeah, and the actual quantum computation course that took us, I actually looked last time, it was 4 lectures to get through that, all of that stuff. So yeah, we kind of breezed through really fast. And today I'm going to talk about some actual quantum cryptography. So stuff that is somewhat related to this course. Recall the big classical cryptographic protocols we looked at during the course. I think you spent probably a bit of time on RSA was one of them. And RSA hinged essentially on the difficulty of factoring. So as long as factoring is difficult and can't be done efficiently, then RSA should work as a protocol. And I think the other big one you spent a lot of time on was probably algamel. And that one hinged on the difficulty of the discrete logarithm. So if discrete log is hard, then we can use algamel. If factoring is hard, we can use RSA. If we run into a situation where either or both of these could be done efficiently, then all of a sudden RSA and algamel become very weak cryptographic systems, and we might be in a little bit of trouble. So luckily, that definitely isn't going to happen. There's no chance that anyone ever is going to find efficient algorithms to do these things. That's exactly what Peter Shor did in 1994. He showed that there are quantum algorithms. The one that we looked at, or you look at most, is his factoring algorithm, but he did find algorithms that make both of these problems easy on quantum computers. Shucks. Yeah, this guy, Peter Shor, he appears a lot. Quantum computation. Really, really big name. But what that kind of means is if we get access to large-scale quantum computers that can run algorithms on a large-scale basis, RSA and algamel might be in trouble. But fear not, the boat is not yet sunk, because with quantum computation, with quantum computers, we have access to new quantum protocols. And one of them is the BB84 protocol. It was proposed by Bennett and Brassard. In 1984. So that's where the BB84 comes from. But before I launch into that protocol, I'd like to just take a few minutes to review a few things about quantum states and quantum bases, and then measurements. So recall that our quantum state, which we denoted, or our general state we denoted with a ket psi, is equal to alpha ket 0 plus beta ket 1. Remember, ket 0 is just the vector 1, 0. Ket 1 is just the vector 0, 1. And these are similar to, if you've taken physics 1 or physics 2, these are similar to I hat and j hat. So these are kind of just the unit vectors in the coordinate plane. So draw that here. We have ket 0 lies right here. Ket 1 lies right here. Does that make sense to everyone, pretty much? So essentially what we're dealing with is we can write a general quantum state as just a linear combination of these two unit vectors. And then recall the other condition that we have is that the inner product of a state with itself has to equal 1, which is to conserve probability, essentially. We know that if we take a measurement in the rectilinear basis, we're going to get ket 0 with probability equal to the norm of alpha squared, and ket 1 with probability equal to the norm of beta squared. So what this condition here does is it just enforces that the sum of these two probabilities is equal to 1. Yeah, and then alpha and beta also, they can be complex numbers. They don't necessarily have to be real. So we've kind of just been shoving that a little bit, sweeping it under the rug, but that's fine. So then recall that we also mentioned another basis, and that was the diagonal basis that had basis states ket plus is 1 over root 2 ket 0 plus ket 1. So what that is we take this ket 0, we add a ket 1 to it, so we get a vector that looks something like this. Plus, and then ket minus is equal to 1 over root 2 ket 0 minus ket 1. So we take this ket 0 and then we add negative ket 1 to it. So we get a vector that looks something like this, ket minus. And then notice that these two vectors are orthogonal to each other. So we take the inner product of ket plus with plus and minus, we get 0, and then we take the inner product of either plus or the minus with itself, we get 1. This one here is normalization, this one here is orthogonality. Then the same kind of thing holds with, if we take the inner product of 0 and 1, we get 0, but if we take the inner product of the 0 state or with itself or the inner product of the 1 state with itself, we get 1. Okay. So now another thing that we can do is notice that ket 0 we could get by taking this ket plus here and this ket minus and adding them together. The horizontal components add together, the vertical components cancel out, and then we just have to throw a constant out front to keep normalization. But this is going to be 1 over square root of 2 ket plus ket minus, and then similarly, ket 1 can be represented as 1 over square root of 2 ket plus minus ket minus. And this is just representing the rectilinear basis states and the diagonal basis. This is a representation of the diagonal basis states and the rectilinear basis. Does that make sense? Are there any questions on that? Okay. So I want to talk just a little bit more about measurement. So suppose we have a state, let's say it's alpha ket 0 plus beta ket 1. It's in the rectilinear basis, and say I want to make a rectilinear measurement. So I feed it into a rectilinear measurement box. What we're going to get out the other end, we can either get a ket 0 or a ket 1. 0 or 1. And essentially what measurement does is say that this is our general state, something like this. When we measure it in a basis, we force it to snap to one of those two basis states. So if we measure a ket 1, what we're really doing is we're taking the state and forcing it to take a stand on ket 1, and it becomes ket 1. If we measure ket 0, similarly, we just snap it down to the ket 0. And then the probabilities at which it'll do that is given by the norm squared of these coefficients. So the probability here of 0 is equal to the norm of alpha squared. The probability 1 is equal to the norm beta squared. And then if we wanted to do a measurement in the diagonal basis, we could do it similarly, but instead of snapping to the ket 0 and ket 1, it would snap to either ket plus or ket minus, one of those diagonal basis states. So we would represent our state in terms of the diagonal basis states, and then from there we figure out our probabilities. So it'd be something like, let's see. We have slightly different coefficients out in front, and then just in terms of ket plus and ket minus. All right. So I think an interesting question that might come up is, okay, so say we measure our qubit, we find that it's in the state ket 0. What happens, or what do you think happens if I immediately make another measurement in the rectilinear basis? Any guesses? Got it. We've got our state. We make a measurement, which we're saying forces it into ket 0 state. So after our measurement, it becomes this. Then what do you think happens if we measure it in that basis again? Exactly. Because now that we've snapped it to this basis state, if we measure in this basis again, it's completely on that basis state. Exactly. So here, if we measure in the rectilinear basis, we just get ket 0 100% of the time. And then similarly, if instead of giving us ket 0, our first measurement gave us a ket 1, then if we measure again in the rectilinear basis, we get ket 1. Okay. So now let's see what happens if we alternate our measurement basis. So what if instead of measuring here in the rectilinear basis, I want to measure in the diagonal basis? So I start with the state ket 0 plus beta ket 1. I measure in the rectilinear basis. We've got two possible outcomes, ket 0, 1. Probabilities alpha squared and norm of beta squared. Now what happens if I take this guy, say we get ket 0 as our measurement, and I want to measure this in the diagonal basis? Or pictorially, we have our state and then we snap it to this guy, so it now looks like this. And then we want to measure in this basis, ket plus, ket minus. Does anyone want to venture a guess as to what might happen with this measurement? Like, what do you think we could possibly get? We're now measuring in the diagonal basis, right? So we want to figure out what our state is in terms of the diagonal basis states. So we have ket 0, which we saw up here is 1 over root 2 times ket plus ket minus. So 1 over root 2 ket plus plus cat minus. And what we see here is we have a uniform superposition of both of the two diagonal basis states. So we could measure either a cat plus or a cat minus, both with probability 1/2. And that comes from the fact that the coefficient in front of the cat plus is 1 over root 2. So the norm squared of that is just 1/2, and then same with the cat minus. So if we measure one of our rectilinear basis states, and if we do this for cat 1, it was 1 over root 2 cat 0 minus cat 1. So we get the same, we could either get cat plus with probability 1/2 or cat minus with probability 1/2. So if we take one of our rectilinear basis states and measure it in the diagonal basis, we've got a 50-50 chance at measuring either a cat plus or a cat minus. So now, suppose I look at this cat plus. Say our chain is, we start with our state and say we measure a cat 1, and then in the rectilinear basis, and we say, oh, we want to measure in the diagonal basis. We measure a cat plus in the diagonal basis. And this is just, for example, this isn't the way it has to go. But now say I want to line up another rectilinear measurement. Does anyone have a guess as to what you think we might get? Up here, we measured at cat 1 in the rectilinear basis, and then here we measured at cat plus in the diagonal. How about this? Raise your hands if you think we could potentially measure a cat 0. Raise your hand if you think we could potentially measure a cat 1. Raise your hand if it's 8 in the morning, you just don't feel like raising your hand. Fair enough. Fair enough. Okay, so let's kind of do the same thing we did up here, where we represent our basis state, the cat plus, in terms of the rectilinear basis. So remember, this is 1 over root 2 cat 0 plus cat 1. And all of a sudden, we have an equal superposition of our two rectilinear basis states, cat 0 and cat 1. So what we could measure cat 0 with probability 1/2, or we could measure cat 1 with probability 1/2. So let's say we measure cat 0. Let's just say it goes down this path. And what we notice is we make a measurement in the rectilinear basis, we get cat 1. Then we inject a diagonal basis measurement, and then make another rectilinear basis measurement, and we get cat 0. So by injecting this diagonal basis measurement, we're able to sometimes measure cat 1 with one rectilinear basis measurement and then a cat 0 with a different measurement. Whereas remember up here, if we just stack rectilinear basis measurements, we're going to keep getting the same thing, because cat 0 in the rectilinear basis is just cat 0. Does that make sense? There any questions on that? Okay. So if I guess the long and short of it is, if we keep measuring in the same basis, subsequent measurements are going to yield the same result. But if we inject a different basis measurement, then we may get different results after we measure in the same basis as we did the first time. So alternating measurements can yield funky results. So how can we use this? This seems like an interesting result. There must be some way that we can apply it, right? And this is where the BB84 protocol comes in. And essentially what we're going to do is we're going to send a bunch of qubits from Alice to Bob, and Alice will prepare them in one basis, Bob will measure them in his basis. And if Bob's basis measurement matches the basis that Alice picked to send the qubit in, they should end up with the same result. If we have an eavesdropper in the middle who's making measurements, if the eavesdropper picks the wrong basis to measure in, then that could cause the results on Alice and Bob's end to be different. And using that, we'll be able to detect eavesdroppers. So let's see how this protocol works. The setup, kind of a classic cryptographic setup. You've got Alice and Bob, and they have some data that they want to share. They have something that they want to do, but they want to do it safely. They don't want anyone spying on them. Eve is evil and wants to spy on them. So now suppose they have a quantum channel down here that allows Alice to send qubits to Bob. And of course, Eve is quantum wiretapping. So she has access to this qubit. She can do whatever she wants with the qubit when it gets to her, and then she shoves it back into the channel, and then it'll go off to Bob. Now, also suppose that they have a classical broadcast channel. So they can just send anything to each other. Anyone can kind of see what's going on in there, including Eve, who's also wiretapping this one. It's like maybe Alice and Bob are sharing a radio, and Eve's got like the radio up to her ear on Alice's frequency or something. Okay. And then the outline of the protocol. The first thing that is going to happen is Alice chooses a random sequence of n bases that are either rectilinear or diagonal. So let's just generate a random sequence. I don't know, what are your guys' favorite basis? Anyone? Or if you don't have a favorite basis, what's the first random basis you think of? Sure. Okay, we got a rectilinear. All right, I'll go. I'll put in a rectilinear. Let's do diagonal. Perfect. Okay. Now let's see if we can get like 10 or 11 of these. Anyone else want to contribute a basis? The floor is open. All right, fine. I'll put in another rectilinear. All right, Lou, do you want to just, you and I can. All right, perfect. 1, 2, 3. Now let's just throw an R at the end for good measure. Okay. So we have now our just random sequence of bases. And then what Alice is going to do is she's going to prepare a bunch of random basis qubits based on this sequence. So for the rectilinear maybe she chooses 0. Then for the second rectilinear, does anyone have a favorite rectilinear basis state? 0, 1? Anyone? I'm sure. Cat 1. Then diagonal basis. Anyone have a least favorite diagonal basis state? Plus, minus? Minus, sure. Then rectilinear. Anyone have a least favorite rectilinear basis state? 0, 1? Let's go with a 1. Then diagonal, maybe throw a plus in there, another diagonal. Yes. And what? Oh, okay. So 3 straight rectilinear. 0, diagonal, cat minus, rectilinear. Luke, what's your favorite rectilinear? You like 1. Okay, nice. All right. So Alice just prepares a bunch of qubits that are in these basis states according to her random sequence. Then the next thing she does is she sends the qubits across the quantum channel to Bob. And then so we take all of these and we just got qubits. We send them through the channel, and then Bob is going to get a bunch of qubits out at the other end. So what Bob is going to do is he's going to choose his own random sequence. And then he's going to use his own sequence to measure Alice's qubits. All right. So it's time to let's generate another sequence of measurements or bases. So how about we start with rectilinear? Everyone happy with that? Okay, and then obviously the next 10 are all diagonal, as is how random numbers work. If anyone wants to contribute one, feel free to jump in at any point. D, 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 R, D. Okay, 1, 2, 3. There we go. So Bob chooses his own sequence, and then he uses that sequence to measure the qubit. So let me just copy the qubits down here. And for now, let's assume that there's no eavesdropper. So for now, Bob is going to take, okay, so this one, I was using orange for, yeah, I was using orange for rectilinear. Okay. So it's going to measure, let's, and the others were in the diathesis. So as the qubits come in one by one, Bob just goes through his sequence and makes measurements in the basis that he chose. So the first qubit comes in, he makes a rectilinear measurement. Second qubit comes in, he makes diagonal measurement. And then this process continues until all the qubits have come in and he's made all his measurements. So now, if you measure ket 0 in the rectilinear basis, can anyone tell me what you get? Or what you can get? Maybe it'll help if I redraw our little diagram. Here. Let's count. So if I want to snap this ket 0 to either ket 0 or ket 1, which one am I going to get? If I measure this in the, or ket 0 in the green basis. Exactly. Because we're already in the rectilinear basis. It's already 100% at ket 0. So if I measure in that basis, I get ket 0. Okay. If I measure ket 1 in the diagonal basis, measure this one, I could get either ket plus or ket minus, because remember, we have an equal superposition. I guess it'd probably be the ket plus or negative ket minus, but either way, we can snap either to this guy or to this guy. So let's just say we snap to ket plus. Ket minus in the diagonal basis. So we're trying to measure this guy in the red basis. Can anyone tell me what we're going to get there? Would you agree with me if I said it was ket plus? Right, exactly. Since ket minus is already in the diagonal basis, if we measure it again, we get ket minus. Ket 1 in the diagonal basis, we could get either ket plus or ket minus in this case. Let's just say we get ket minus. Ket plus in the diagonal basis, ket plus. Ket minus in the rectilinear basis. So we have the ket minus, we're trying to snap it to either the ket 0 or the ket 1. Our ket minus is an equal probability of ket 0 and ket 1, so we could get either. Luke, what do you say we get for this one? Let's say we get 1. Perfect. Okay. Ket 1. Ket 0 in the diagonal basis. Again, ket 0 is equal probability ket plus, ket minus. Let's just go ket minus here. And then we measure ket 1 in the rectilinear basis, get ket 1, measure ket 0, rectilinear basis, ket 0, minus in the rectilinear basis, we could get either ket 0 or ket 1. Let's go ket 0 this time. And then if we measure ket 1 in the diagonal basis, we could get either ket plus or ket minus. Let's see, do we have we do have an imbalance, so I'll just go ket plus. I definitely chose those very randomly. Notice that we have two kind of cases here in this sequence. We have the cases where the measurement that Bob, or the gate that Bob measured with, and the state that Alice prepared are in the same basis. We see that happen here. Let's see. Here. 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 I think that's it. And in these cases, notice that the state that Alice has and the state that Bob has always match. Then in the other cases, we've got Alice's qubit was prepared in one basis, Bob measured in a different basis. So these, there's kind of no correlation. You get 50-50 ket plus, ket minus. So what they do with this is they then, this step 5? Yeah, this is step 5. they are going to broadcast the basis sequence that they chose. And then when they both look at the basis sequences, they'll know, okay, for instance, here we matched up on R here, we matched up on the D here, we matched up on these two R's. Am I missing one? Yes, and this D here. So on these 5 bases we matched, so we will have measured the same thing in those 5 qubits. And what they'll do is they will take these qubits, and they'll have noted down what their measurements were, and they'll use that to create their bit string. So, ket 0 and ket 1, you probably assign a 0, 1, and then ket plus, ket minus, you just choose one of them to be 0, the other one to be 1. And then they both, from Alice preparing the states and Bob from measuring them in the same basis, have the same sequence of bits that they can now use to do whatever their cryptographic protocol is. They have a shared secret key. And all that they had to share publicly on the broadcast channel was their sequence of bases, which, if you're randomly generating the states in those bases, there's not really much you can do with that. Are there any questions on this? Okay. So now, what happens if Eve decides to look at our quantum channel? So what if Eve gets involved? Say you're trying to eavesdrop on my quantum channel. So I send a qubit, and you're able to pick up the qubit, do whatever you want with it before sending it off to Bob. What do you think? What would you try doing with the qubit to gain some information about it? Take a measurement of the qubit. Right. So one of the thing Alice can do, she can measure the qubit. So let's see what happens if Alice decides to measure the qubits. She gets involved. So let me just copy the states down. I'm just going to use the same sequence of basis, or the same basis sequence for Alice and Bob. But now, how does Eve decide which basis to measure in? As the qubits are coming along, she doesn't have access to Alice's basis sequence. She doesn't have access to Bob's basis sequence because they're keeping them private until they've measured all the qubits. So what can Eve do? How can Eve handle that? Right now, she's kind of hunting in the dead of night. All she can really do is kind of shoot around blindly, hoping to hit something. So she chooses just a random sequence. So let's generate a random sequence for each. Luke, you want to help me out with this? Yeah. Let's start with diagonal. Here. Okay. All right, perfect. So this is going to be Eve's sequence. These are the measurements that she makes. So she's going to measure this one linear, measure this one rectilinear. Let's diagonal, 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 linear, diagonal, linear, diagonal, diagonal. Okay. Okay. So in the first case, she measures ket 0 in the diagonal basis, and we could either get ket plus or ket minus in this case. Let's just say we get ket minus. I think is a fair one to go with. Ket 1 in the rectilinear basis is already in the rectilinear basis, so we just get the same result. Ket minus in the rectilinear basis, we could get either ket 0 or ket 1. Let's go ket 0. Ket 1 in the diagonal basis, ket plus or ket minus, again, equal superposition. So let's just go ket plus. Ket plus in the diagonal basis, we're guaranteed to get ket plus. Ket minus in the diagonal basis, we're guaranteed to get ket minus. Ket 0 in the rectilinear basis, guaranteed to get ket 0. Ket 1 in the diagonal basis, we can get either ket plus or ket minus, say ket plus. Ket 0 in the rectilinear basis, we are guaranteed to get ket 0. Then ket minus, diagonal basis, guaranteed ket minus. Ket 1 in the diagonal basis, we could get either ket plus or ket minus. So let's go just ket minus. Okay, so these then are the sequence of qubits that Eve is going to send to Bob after she measures one, sends it to Bob, it's going to be the ket minus. She measures the second one, sends it to Bob, it's going to be ket 1. And then Bob is going to take his measurements. So let me see if I can copy only the gates down. Yeah, there we go. That should be fine mostly. Yeah, okay. Except so then Bob makes his measurements. First case, he measures ket minus in the rectilinear basis. He could get either ket 0 or ket 1. Ket 1 here, say he gets ket 1. Ket 1 in the diagonal basis could be ket plus or ket minus. Let's go ket plus. Ket 0 in the diagonal basis, same as before, could be either ket plus or ket minus. Let's go ket minus. Ket plus in the diagonal basis gives us ket plus. Ket plus in the diagonal basis gives us ket plus. Ket minus in the rectilinear basis could be either ket 0 or ket 1. Let's go ket 0. Ket 0 in the diagonal basis, ket plus or ket minus, go ket minus there. Ket plus in the rectilinear could be ket 0 or ket 1, ket 0. Ket 0 in the rectilinear, since it's already in the rectilinear basis, we just get the same thing. Ket minus in the rectilinear basis could be ket 0 or ket 1. Let's go ket 1. And then ket minus in the diagonal basis, just going to be ket minus. Okay, so now we have the sequence of qubits after Bob makes the measurement, and he marks down these results. So then Alice and Bob share their sequence of bases. And okay, they see we line up on where these red ones are. So we should have the same results for all of these guys. And if you look here, in this case, sure they do. In this case, they do. In this case, they do. But look what happens right here. Alice starts with ket 0. Then Eve chooses the wrong basis to measure in, measures in the diagonal basis, gets ket minus. And then Bob measures in the correct basis, the rectilinear basis. But now that this is a ket minus instead of a ket 0, we've reopened, there's a 50-50 probability of it being either ket 0 or ket 1. Bob measures ket 1. So Alice and Bob know that they have to match if there's no one watching their wire, but they do not match. Alice has ket 0, Bob has ket 1. So what they can do to detect an eavesdropper is they take some somewhat large subset of the ones where they match up and then just share, hey, here's what I got in my measurement. Or like Bob will share, here's what I got in my measurement with Alice, and then Alice will kind of look at them and verify them. And if they're all the same for a sufficiently large subset, then you're probably good. Probably wasn't an eavesdropper. But if you are getting a bunch that don't match, then your wire was being tapped and you have to abort the protocol probably. So and then if you detect that there was no eavesdropper, then you take the ones that you didn't send across and you just use those to create your secret string. And then suppose there is an eavesdropper, and for a spot where the bases match, we have a 50-50 chance of picking the wrong measurement basis, and then a 50-50 chance, given the wrong measurement basis, of Bob's measurement being wrong. So overall, you have a 1 in 4 chance or a 25% chance of getting caught as the eavesdropper. So you have a 3/4 chance of getting away, which seems high. But then if we stack on a ton of instances of it, then it's, 3/4 chance times a 3/4 chance times a 3/4 chance, which goes down. So you could make the probability of an eavesdropper getting away with it arbitrarily low by just increasing the number of qubits that you send. Are there any questions on that? So obviously, eavesdropping by just taking measurements, Eve's going to get caught, more likely than not. So is there anything else that you could think of that Eve could maybe do in order to gain information about the qubit without messing with it? Like she can do anything that she wants with this qubit while she has it. Exactly. What if Eve has access to the Kaminoan cloners and takes the qubit, says, oh, you know what I want to do? I just want to make a second qubit just like it, and then send the qubit back to Bob, grab the second qubit, let's make a copy of it, and she can generate her own sequence of qubits that are the same as the ones Alice sent, and then wait for Alice and Bob to broadcast their measurement bases. And then once she's done that, she knows exactly what basis to measure it. If that's possible, then the protocol's in danger. So I should probably talk about the no cloning theorem. So suppose that there is a gate, let's call it K, And this is our hypothetical clone gate. And the way that we want this gate to behave is if we take in ket plus tensored with some other state, let's call it ket s, where ket plus is the state that we're trying to clone, ket s is just some other state that we throw in there that we clone it into. We want this to give us ket plus tensored with ket plus, and then the k gate on, say, ket 0 tensored with ket s is equal to ket 0 tensor ket 0. So essentially what this is saying is we apply this gate to ket plus and then some other qubit, and we get two ket pluses out the other end. We've cloned our ket plus. And here we throw in ket 0 tensored with just some other state s, and we get ket 0 tensored with ket 0. And let me call this state here big psi, and let me call this state here big phi. And essentially what I'm going to do is I'm going to use an argument where we take the inner products of these states with each other and then the inner product of these states with each other. Because this state here and this state here are the same state. This state here and this state here are the same state. And if I take the inner product of big psi and big phi, I should get the same thing. And what I'm going to show is essentially if this k gate exists, then we get different values for the inner products of these two things. So our cloning gate can't exist. Fortunately or unfortunately, depending on your opinion of cloning. Okay, let's start with these two guys first. So this inner product is equal to the bra of psi, remember, is just the conjugate transpose of the ket. So ket psi conjugate transpose times ket phi, which is equal to k ket plus tensor ket s conjugate transpose times k 0 tensor ket s. And then the conjugate transpose, we just distribute and then reverse. So this is equal to ket plus tensor ket s conjugate transpose times k conjugate transpose times k ket 0 tensor ket s. Now, a nice thing to note about the tensor product is if you have, say, ket alpha tensor ket beta, where actually, let me use psi 1 and little psi 1, little psi 2. You take the conjugate transpose of this, you just get this guy. So you change the kets to bras, but keep the order of the tensor product the same. It's another beautiful thing about bracket notation. But here, what this gives us is it just gives us this times k conjugate transpose k ket 0 tensor ket s. But remember that our quantum gates are unitary. So this is a unitary gate, and then the unitary came from we have to preserve inner product. I talked about that a bit last time, but essentially the restriction on the quantum gates that we saw was if k is a quantum gate, then the conjugate transpose of k times itself has to equal the identity matrix. So either of these have to equal the identity. So this guy down here is just the identity matrix, and we're left with this inner product is equal to cat plus tensor S, or I guess bra plus tensor bra S times cat 0 tensor cat S. And another nice thing about the tensor product is if we have something like this where you have a tensor B times C tensor D, it's the same thing as AC tensored with BD. So we just multiply these guys together and multiply these guys together. So we take cat plus and cat 0, or the bra plus and the cat 0, we match them together. So bra plus cat 0, tensor, and then bracket S. Now, another thing to note here is these are both scalars. Inner product just gives you scalar number. So the tensor product of two scalars is just the same as the normal multiplicative product. So we can kind of ignore the tensor product here. Just pretend that doesn't exist. And we just get the product of this inner product and this inner product. Now, can anyone tell me what the inner product of S with itself is? 1. Right, exactly. Because of normalization. Now, here's an interesting question. This is 1 if S and S are the same state, right? So if this S is the same as this S. Why am I kind of assuming here that they're the same S? Like what if Eve picks a different S for cloning cat plus and cloning cat 0? Yeah, but then I think also the bigger thing here is Alice doesn't know whether she has cat plus or cat 0, right? So if she can't really choose a different state to use as the second state because she has no clue which one she's trying to clone. Yeah. So this is just 1 because these are the same state. So then let's take a look at this guy here. Remember, cat plus 1 over root 2, cat 0 plus cat 1. So bra plus is going to be 1 over root 2, bra 0 plus bra 1. So this inner product becomes 1 over root 2, 0 plus 1 times cat 0, 1 over root 2, inner product of 0 itself, plus inner product of 1, 0. Recall that this guy is 0 because of orthogonality, and this guy is 1 because of the normalization condition. So we see that this guy is equal to 1 over square root of 2. And that's if we take the inner product of these two guys. Now what happens if we take the inner product of these two guys? So that's inner product of big psi and big phi. So we're taking the inner product of the same two states. In this case, it's cat plus, and then cat 0, cat 0. Collecting these guys together is inner product of plus and 0 times the inner product of 0. Again, since we're working with scalars, the tensor product is just the same as multiplicative product. And then remember that this guy here, we just found here is equal to 1 over root 2. So we get that this is equal to 1 over root 2 times 1 over root 2, which is 1/2. These guys are different. So we're taking the inner product of the same two states and we get a different value, which can't happen. We arrive at a contradiction and we see that our gate K can't exist. So Eve is not able to just clone the qubits. And then I think through a similar argument, you could show even that she's not able to gain any information without modifying the original qubit. So to gain any information about the system, Eve has to potentially modify the qubit in some way. Up here we saw via taking a measurement, and that makes her detectable. So are there any questions on any of that? Yeah, that's essentially the BB84 protocol. Is Alice takes a bunch of qubit or declares a basis, or comes up with a sequence of bases. Then she prepares a bunch of qubits in that basis sequence, sends the qubits to Bob, and then Bob measures them. They take a subset of the results where their bases match. They compare answers, and then if everything's the same like it should be, there's no eavesdropper. If there are some discrepancies, then you've detected that there was an eavesdropper messing with your channel, and you abort at least that segment of protocol. Then it could get kind of weird if you have a sequence where you see heavy instances of eavesdropping, and then maybe there's a sequence later where you don't see any eavesdropping. There it might get kind of weird, but that's the BB84 protocol. A little bit on quantum cryptography. Any questions on anything, or anything from last lecture too? Because I kind of breezed really fast through stuff last time. See, quantum's not that scary. It's just linear algebra and measurements. Lots and lots of measurements. That's all I've got. So you guys are free to go if you'd like. Is that 12 minutes to spare? Yeah, I probably shouldn't talk about Hadamard teleportation. Probably not. So good luck with finals and getting through the rest of classes. So. And if anyone has any questions, I'll be here for another 5 minutes or so because we got the time.